Introduction to Software Engineering. Software engineering is intended to support professional software development rather than individual programming. It includes techniques that support program specification, design, and evaluation, none of which are normally relevant for personal software development. Many people think that software is simply another word for computer programs. However, when we are talking about software engineering, software is not just the programs themselves but also all associated documentation and configuration data that is required to make these programs operate correctly. Professionally developed software system is often more than a single program. The system usually consists of a number of separate programs and configuration files that are used to set up these programs. It may include system documentations, which describes the structure of the system, user documentation, which explains how to use the system, and websites for the user to download recent product information. This is one of the important differences between professional and amateur software development. If you are writing a program for yourself, no one else will use it and you don't have to worry about writing program guides, documenting the program design, etc. However, if you are writing software that other people will use and other engineers will change, then you usually have to provide additional information as well as the code of the program. First, let's see what is a software. Software is considered to be a collection of executable programming code, associated libraries, and documentation. Software when made for a specific requirement is called software product, or computer programs and associated documentation, also known as software. Software products may be developed for a particular customer or may be developed for a general market. But what are the attributes of a good software? Good software should deliver the required functionalities and performance to the user and should be maintainable, dependable, and usable. What is software engineering? Software engineering is an engineering discipline that is concerned with all aspects of software production, or software engineering is the systematic application of engineering approaches to the development of software. What is the difference between software engineering and computer science? Computer science focuses on theory and fundamentals. Software engineering is concerned with the practicalities of developing and delivering useful software. What is the difference between software engineering and system engineering? System engineering is concerned with all aspects of computer-based systems development including hardware, software, and process engineering. Software engineering is the part of this more general process. What are the best software engineering techniques and methods? While all software projects have to be professionally managed and developed, different techniques are appropriate for different types of system. For example, games should always be developed using a series of prototypes, whereas safety critical control system requires a complete and analyzable specification to be developed. You cannot therefore say that one method is better than another. What differences has the web made to software engineering? The web has led to this availability of software services and the possibility of developing highly distributed service-based systems. Web-based systems development has led to important advances in programming languages and software reuse. Let's discuss in detail about the software engineering definition. Software engineering is an engineering discipline that is concerned with all aspects of software production from the early stages of system specification through to maintaining the system after it has gone into use. In this definition, there are two key phrases. Engineering discipline is the first one. Engineers make things work. They apply theories, methods, and tools where these are appropriate. However, They use them selectively and always try to discover solutions to problems even when there are no applicable theories and methods. Engineers also recognize that they must work to organizational and financial constraints, so they look for solutions within these constraints. Second phrase: all aspects of software production. Software engineering is not just concerned with the technical processes of software development, it also includes activities such as software project management and the development of tools, methods, and theories to support software production. Product characteristics. Engineering is about getting results of the required quality within the schedule and budget. This often involves making compromises. People writing programs for themselves, however, can spend as much time as they wish on the program development. In general, software engineering adopt a systematic and organized approach to their work, as this is often the most effective way to produce high quality software. However, engineering is all about selecting the most appropriate method for a set of circumstances, so a more creative, less formal approach to development may be effective in some circumstances. Less formal development is particularly appropriate for the development of web-based systems which require a blend of software and graphical design skills. What is maintainability? Software should be written in such a way so that it can evolve to meet the changing needs of customer. This is critical attribute because software change is an unavoidable requirement of a changing business environment. Dependability and security. Software dependability include a range of characteristics including reliability, security, and safety. Dependable software should not cause physical or economic damage in the event of system failure. Unwanted users should not be able to access or damage the system. Efficiency. Software should not make wasteful use of system resources such as memory and processor cycles. Efficiency therefore includes responsiveness, process timing, memory utilization, etc. Acceptability. Acceptability is also one of the product characteristics. Software must be acceptable to the type of users for which it is designed. This means that it must be understandable, usable, and compatible with other systems that they use. Software process models. A software process model is a simplified representation of a software process. Each process model represents a process from a particular perspective and thus provides only partial information about the process. For example, a process activity model shows the activities and their sequence but may not show the roles of the people involved in these activities. In this section, we will introduce a number of very general process models, sometimes called process paradigm, and present these from an architectural perspective. That is, we see the framework of a process but not the details of specific activities. These generic models are not definitive description of software processes. Rather, they are abstraction of the process that can be used to explain different approaches to software development. You can think of them as process frameworks that may be extended and adopted to create more specific software engineering processes. The process models that we will cover here are the waterfall model, incremental development model, reuse-oriented software engineering model, spiral model, or Boehm's spiral model. The waterfall model. This takes the fundamental process activities of specification, development, validation, and evaluation and represents them as a separate process phases such as requirement specification, software design, implementation, testing, and so on. Incremental development model. This approach interleaves the activities of specification, development, and validation. This system is developed as a series of versions, with each version adding functionalities to the previous version. Reuse-oriented software engineering. This approach is based on the existence of a significant number of reusable components. The system development process focuses on integrating these components into a system rather than developing them from scratch. Boehm's spiral model. This software process is represented as a spiral rather than a sequence of activities with some backtracking from one activity to another. Each loop in the spiral represents a phase of the software process. Thus, the innermost loop might be concerned with the system feasibilities, the next loop with the requirements definition, the next loop with the system design, and so on. These models are not mutually exclusive and are often used together, especially for large system development. For large systems, it makes sense to combine some of the best features of the waterfall and the incremental development models. You need to have information about the essential system requirements to design software architecture to support these requirements. You cannot develop this incrementally. Subsystems within a large system may be developed using different approaches. Parts of the system that are well understood can be specified and developed using a waterfall based process. Parts of the system which are difficult to specify in advance, such as the user interface, should always be developed using an incremental approach. Waterfall model. This model is illustrated in the figure. Because of the cascade from one phase to another, this model is known as the waterfall model or software life cycle. The waterfall model is an example of a plan-driven process. In principle, you must plan and schedule all the process activities before starting work on them. The principal stages of the waterfall model directly reflect the fundamental development activities. 1. Requirements analysis and definition. The system's services, constraints, and goals are established by consultation with system user. They are then defined in detail and serve as a system specification. 2. System and software design. The system's design process allocates the requirement to either hardware or software systems by establishing an overall system architecture. Software design involves identifying and describing the fundamental software system abstractions and their relationships. 3. Implementation and unit testing. During this stage, the software design is realized as a set of programs and program units. Unit testing involves verifying that each unit meets its specification. 4. Integration and system testing. The individual program units and programs are integrated and tested as a complete system to ensure that software requirements have been met. After testing, the software system is delivered to the customer. 5. Operation and maintenance. Normally, this is the longest life cycle phase. The system is installed and put into practical use. Maintenance involves correcting errors which were not discovered in earlier stages of the life cycle, improving the implementation of system units and enhancing the system services as new requirements are discovered. In principle, the result of each phase is one or more documents that are approved. The following phase should not start until the previous phase has finished. In practice, these stages overlap and feed information to each other. During design, problems with requirements are identified. During coding, design problems are found and so on. The software process is not a simple linear model but involves feedback from one phase to another. Documents produced in each phase may then have to be modified to reflect the changes made. Because of the cost of producing and approving documents, iterations can be costly and involve significant rework. Therefore, after a small number of iterations, it is normal to freeze parts of the development such as the specification, and to continue with the later development stages. Problems are left for later resolution, ignored, or programmed around. This premature freezing of requirements may mean that the system would not do what the user wants. It may also lead the badly structured system as design problems are circumvented by implementation tricks. During the final life cycle phase, operation and maintenance, the software is put into use. Errors and omissions in the original software requirements are discovered. Program and design errors emerge and the need for new functionalities is identified. The system must therefore evolve to remain useful. Making these changes may involve repeating previous process stages. The waterfall model is consistent with other engineering process models and documentation is produced at each phase. This makes the process visible so managers can monitor progress against the development plan. Its major problem is the inflexible partitioning of the project into distinct stages. Commitments must be made at the early stage in the process, which makes it difficult to respond to change customer requirements. In principle, the waterfall model should only be used when the requirements are well understood and unlikely to change radically during system development. However, the waterfall model reflects the type of process used in other engineering projects. As it's easier to use a common management model for the whole project, software processes based on the waterfall model are still commonly used. An important variant of the waterfall model is formal system development, where a mathematical model of the system specification is created. This model is then refined using mathematical transformation that preserve its consistency into executable code. Based on the assumption that your mathematical transformations are correct, you can therefore make a strong argument that a program generated in this way is consistent with its specification. The formal approach simplifies the production of a safety and security case. This demonstrates to customer or regulators that the system actually meets its safety or security requirements. Processes based on formal transformation are generally only used in the development of safety critical or security critical systems. They require specialized experts. For the majority of systems, this process does not offer significant cost benefits over other approaches to system development. Incremental development model. Incremental development model is based on the idea of developing an initial implementation, exposing this to user comment and evolving it through several versions until an adequate system has been developed. Specification, development and validation activities are interleaved rather than separate, with rapid feedback across activities. Incremental software development, which is a fundamental part of agile approaches, is better than a waterfall approach for most business, e-commerce, and personal systems. Incremental development reflects the way that we solve problems. We rarely work out a complete problem solution in advance but move toward a solution in a series of steps, backtracking when we realize that we have made a mistake. By developing the software incrementally, it is cheaper and easier to make changes in the software as it is being developed. Each increment or version of the system incorporates some of the functionality that is needed by the customer. Generally, the early increments of the system include the most important or most urgently required functionality. This means that the customer can evaluate the system at a relatively early stage in the development to see if it delivers what is required. If not, then only the current increment has to be changed and possibly new functionality defined for later increments. Incremental development has three important benefits: compared to the waterfall model. 1. The cost of accommodating changing customer requirements is reduced. The amount of analysis and documentation that has to be redone is much less than is required with the waterfall model. 2. It is easier to get customer feedback on the development work that has been done. Customers can comment on demonstrations of the software and see how much has been implemented. Customers find it difficult to judge progress from software design documents. 3. More rapid delivery and development of useful software to the customer is possible, even if all of the functionality has not been included. Customers are able to use and gain value from the software earlier than is possible with the waterfall process. Incremental development in some form is now the most common approach for the development of application systems. This approach can be either plan-driven, agile, or more usually a mixture of these approaches. In a plan-driven approach, the system increments are identified in advance. If an agile approach is adopted, the early increments are identified, but the development of later increments depend on progress and customer priorities. From the management perspective, the incremental approach has two problems. Number one, the process is not visible. Manager needs regular deliverables to measure progress. If systems are developed quickly, it is not cost effective to produce documents that reflect every version of the system. Number two, system structure tends to degrade as new increments are added. Unless time and money is spent on refactoring to improve the software, regular change tends to corrupt its structure. Incorporating further software changes become increasingly difficult and costly. The problems of incremental development become particularly acute for large, complex, long lifetime systems where different teams develop different parts of the system. Large systems need a stable framework or architecture, and the responsibilities of the different teams working on parts of the system need to be clearly defined with respect to that architecture. This has to be planned in advance rather than developing incrementally. You can develop a system incrementally and expose it to the customer for comments without actually delivering it and deploying it in the customer's environment. Incremental delivery and deployment means that the software is used in real, operational processes. This is not always possible as experimenting with new software can disrupt normal business processes. Reuse-oriented software engineering. In the majority of software projects, there is some software reuse. This often happens informally when people working on the project know of designs or code that are similar to what is required. They look for these, modify them as needed, and incorporate them into their system. This informal reuse takes place irrespective of the development process that is used. However, software development processes that focuses on the reuse of existing software have become widely used. Reuse-oriented approaches rely on a large base of reusable software components and an integrated framework for the composition of these components. Sometimes these components are systems in their own right. COTS or commercial off-the-shelf systems that may provide specific functionality such as word processing or a spreadsheet. A general process model for reuse-based development is shown in figure. Although the initial requirement specification stage and the validation stage are comparable with other software processes, the intermediate stages in a reuse-oriented process are different. These stages are component analysis. Given the requirement specification, a search is made for components to implement that specification. Usually, There is no exact match, and the components that may be used only provide some of the functionality required. 2. Requirements modification. During this stage, the requirements are analyzed using information about the components that have been discovered. They are then modified to reflect the available components. Where modifications are impossible, the component analysis activity may be re-entered to search for alternative solutions. System design with reuse. During this phase, the framework of the system is designed or an existing framework is reused. The designers take into account the components that are reused and organize the framework to cater for this. Some new software may have to be designed if reusable components are not available. 4. Development and integration. Software that cannot be externally procured is developed, and the components and COTS systems are integrated to create the new system. System integration in this model may be part of the development process rather than a separate activity process. Before we discuss next topics, let's see the software specifications. Software specification or requirements engineering is the process of understanding and defining what services are required from the system and identifying the constraints on the system's operation and development. Requirements engineering is a particularly critical stage of the software process, as errors at this stage inevitably lead to later problems in the system design and implementation. The requirements engineering process aims to produce an agreed requirements document that specifies system satisfying stakeholders' requirement. Requirements are usually presented at two levels of detail. End users and customers need a high-level statement of the requirements. System developers need a more detailed system specification. There are four main activities in the requirements engineering process. 1. Feasibility study. An estimate is made of whether the identified user needs may be satisfied using current software and hardware technologies. The study considers whether the proposed system will be cost effective from a business point of view and if it can be developed within existing budgetary constraints. A feasibility study should be relatively cheap and quick. The result should inform the decision of whether or not to go ahead with a more detailed analysis. 2. Requirements elicitation and analysis. This is the process of deriving the system requirements through observation of existing systems, discussions with potential users and procurers, task analysis, and so on. This may involve the development of one or more system models and prototypes. This can help you to understand the system to be specified. 3. Requirements specification. Requirements specification is the activity of translating the information gathered during the analysis activity into a document that defines a set of requirements. Two types of requirements may be included in this document. User requirements are abstract statement of the system requirements from the customer and end user of the system. System requirements are more detailed description of the functionality to be provided. 4. Requirements validation. This activity checks the requirements of realism, consistency, and completeness. During this process, errors in the requirements document are inevitably discovered. It must then be modified to correct these problems. Of course, the activities in the requirements process are not simply carried out in a strict sequence. Requirements analysis continue during definition and specification, and new requirements come to light throughout the process. Therefore, the activities of analysis, definition, and specification are interleaved. In agile methods, such as extreme programming, requirements are developed increasingly according to user priorities, and the elicitation of requirements comes from users who are part of the development team. Boehm's spiral model. Boehm's spiral model. A risk-driven software process framework was proposed by Boehm in 1988. This is shown in figure. Here, the software process is represented as a spiral rather than a sequence of activities with some backtracking from one activity to another. Each loop in the spiral represents a phase of the software process. Thus, the innermost loop might be concerned with system feasibility, the next loop with the requirements definition, the next loop with system design, and so on. The spiral model combines change avoidance with change tolerance. It assumes that changes are a result of project risk and include explicit risk management activities to reduce these risks. Each loop in the spiral is split into four sectors. 1. Objective setting. Specific objectives for the phase of the project are defined. Constraints on the process and the product are identified and a detailed management plan is drawn up. Project risks are identified. Alternative strategies depending on these risks may be planned. 2. Risk assessment and reduction. For each of the identified project risks, a detailed analysis is carried out. Steps are taken to reduce the risk. For example, if there is a risk that the requirements are inappropriate, a prototype system may be developed. 3. Development and validation. After risk evaluation, a development model for the system is chosen. For example, throwaway prototype may be the best development approach if user interface risks are dominant. If safety risks are the main consideration, development based on the formal transformation may be the most appropriate process, and so on. If the main identified risk is subsystem integration, the waterfall model may be the best development model to use. 4. Planning. The project is reviewed and a decision made whether to continue with a further loop of the spiral. If it is decided to continue, plans are drawn up for the next phase of the project. The main difference between the spiral model and the other software process models is its explicit recognition of the risk. A cycle of the spiral begins by elaborating objectives such as performance and functionality. Alternative ways of achieving these objectives and dealing with the constraints on each of them are then enumerated. Each alternative is assessed against each objective and source of the project risk are identified. The next step is to resolve these risks by information gathering activities such as more detailed analysis, prototyping, and simulation. Once risks have been assessed, some development is carried out, followed by a planning activity for the next phase of the process. Informally, risk simply means something that can go wrong. For example, if the intention is to use a new programming language, a risk is that available compilers are unreliable or do not produce sufficient efficient object code. Risks lead to proposed software changes and project problems such as schedule and cost overrun. So, risk minimization is very important project management activity. User interface design. User interface is the front-end application view which user interacts in order to use the software. The software becomes more popular if its user interface is attractive, simple to use, responsive in short time, clear to understand, consistent on all interface screens. There are two types of user interface: command line interface and graphical user interface. Command line interface provides a command prompt where the user types the command and feeds to the system. The user needs to remember the syntax of the command and its use. Graphical user interface provides the simple interactive interface to interact with the system. GUI can be a combination of both hardware and software. Using GUI, user interrupts the software. User interface design process. The analysis and design process of a user interface is iterative and can be represented by a spiral model. The analysis and design process for user interface consists of four framework activities. 1. User task environmental analysis and modeling. Initially, the focus is based on the profile of users who will interact with the system, such as understanding, skill, and knowledge, types of user, etc. Based on the user's profile, users are made into categories. From each category, requirements are gathered. Based on the requirements, developer understand how to develop the interface. Once all the requirements are gathered, a detailed analysis is conducted. In the analysis part, the tasks that the user performs to establish the goals of the system are identified, described, and elaborated. The analysis of the user environment focuses on the physical work environment. Among the questions to be asked are: where will the interface be located physically? Will the user be sitting, standing, or performing other tasks unrelated to the interface? Does the interface hardware accommodate space, light, or noise constraints? Are the special human factors considerations driven by environmental factors? Interface design. The goal of this phase is to define the set of interface objects and actions, such as control mechanisms that enable the user to perform desired tasks, indicate how these control mechanisms affect the system, specify the action sequence of tasks and subtasks, also called a user scenario, indicate the state of the system when the user performs a particular task. Always follow the three golden rules stated by Theo Mendel. Design issues such as response time, command and action structure, error handling, and help facilities are considered as the design model as refined. This phase serves as the foundation for the implementation phase. Phase 3. Interface construction and implementation. The implementation activity begins with the creation of prototype that enables usage scenario to be evaluated. As iterative design process continue, a user interface toolkit that allows the creation of windows, menu, device interaction, error messages, command, and many other elements of an interactive environment can be used for completing the construction of an interface. Phase 4. Interface validation. This phase focuses on testing the interface. The interface should be in such a way that it should be able to perform tasks correctly and it should be able to handle a variety of tasks. It should achieve all the user's requirement. It should be easy to use and easy to learn. Users should accept the interface as a useful one in their work. Golden rules. The following are the golden rules stated by Theo Mendel that must be followed during the design of the interface. Place the user in control. Define the interaction modes in such a way that does not force the user into unnecessary or undesired actions. The user should be able to easily enter and exit the mode with little or no effort. Provide for flexible interaction. Different people will use different interaction mechanisms. Some might use keyboard commands, some might use mouse, some might use touchscreen, etc. Hence, all interaction mechanisms should be provided. Allow user interaction to be interruptible and undoable. When a user is doing a sequence of actions, the user must be able to interrupt the sequence to do some other work without losing the work that had been done. The user should also be able to do undo operation. Streamline interaction as skill level advances and allow the interaction to be customized. Advanced or highly skilled user should be provided a chance to customize the interface as user wants, which allows different interaction mechanisms so that user does not feel bored while using same interaction mechanism. Hide technical internals from casual users. The user should not be aware of internal technical details of the system. He should interact with the interface just to do his work. Designed for direct interaction with objects that appear on screen, the user should be able to use the objects and manipulate the objects that are present on the screen to perform a necessary task. By this, the user feels easy to control over the screen. Reduce the user's memory load. Reduce demand on short-term memory. When users are involved in some complex task, the demand on short-term memory is significant. So the interface should be designed in such a way to reduce the remembering of previous done actions, given inputs and results. Establish meaningful defaults. Always initial set of defaults should be provided to the average user. If a user needs to add some new features, then he should be able to add the required features. Define shortcuts that are intuitive. Mnemonics should be used by the user. Mnemonics means the keyboard shortcut to do some action on the screen. The visual layout of the interface should be based on a real-world metaphor. Anything you represent on screen, if it is a metaphor for real-world identity, then user would easily understand. Disclose information in a progressive fashion. The interface should be organized hierarchically, such as on the main screen the information about the task, an object or some behavior should be presented first at a high level of abstraction. More detail should be presented after the user indicates interest with a mouse pick. Make the interface consistent. Allow the user to put the current task into a meaningful context. Many interfaces have dozens of screens, so it is important to provide indicators consistently so that the user know about the doing work. The user should also know from which page has navigated to current page, and from the current page where can navigate. Maintaining consistency across a family of applications. The development of some set of applications all should follow and implement the same design rules so that consistency is maintained among applications. If past interactive models have created user expectation, do not make changes unless there is a compelling reason.